Radiant is a startup developing Kaleidos, a portable 1.2 megawatt microreactor. Kaleidos can be up and running within an hour, replacing diesel generators used by remote communities, backup power, or relief during disaster scenarios. Our reactor is being designed with SimEngine, our in-house tool fusing reactor digital twins with aerospace-derived, hardware-in-the-loop simulators. Let's take a look inside Kaleidos to see how this capability accelerates reactor and control systems development. Kaleidos produces heat through a controlled fission chain reaction in the graphite moderated core. A compressor forces helium through the core in the primary loop. Helium is an inherently safe heat transfer fluid because it doesn't become radioactive. The primary loop transfers heat to a supercritical CO2 Brayton cycle, producing power in response to customer load. The fission reaction is controlled by the motion of 16 control drums in a ring around the core, each containing an arc of neutron poison. Meltdown-proof trisul fuel particles are arranged in compact cylinders stacked in fuel channels. State-of-the-art multi-physics modeling tools from the Department of Energy's NEAMS program are used to produce high-accuracy estimates of reactor criticality, fuel performance, and temperature distribution under a range of operating conditions. Reduced order models derived from these high-fidelity outputs allow real-time simulation of the reactor and its control system with SimEngine. SimEngine's real-time modeling capability enables direct coupling with physical systems, demonstrated here by the integration of a control drum into the sim. Position commands are sent to the drum, while its real position is encoded and fed back into the system. Any mismatch between the physical and simulated system is used to improve modeling fidelity, allowing for rapid risk buy-down. As it runs, the simulation is keeping track of all reactor temperatures, including the core, its control drums, and the pressure vessel. An air jacket allows direct passive cooling of the pressure vessel under fault scenarios. Insulation reduces heat leak under normal operation and allows for the use of low-temperature, cost-effective shielding materials. Parameters such as core reactivity, vessel and fuel temperatures, and output power are plotted alongside the simulation. SimEngine will now demonstrate integrated execution of the reactor digital twin with its real-time control system as it goes through a startup. Drums are rotated to insert reactivity until criticality is achieved. At this point, the neutron population starts growing exponentially. When the core starts to heat up due to the release of fission energy, the control system further turns the drums in order to maintain criticality. The drums move by an additional 30 degrees to offset the core's negative temperature feedback coefficient. The turbo machinery ramps up to speed as the core reaches target temperature, and a circuit breaker connects the microgrid electrical load. Unlike traditional nuclear power plants, Kaleidos is capable of rapid load throttling, or efficiently following a fluctuating electric demand. This is accomplished by adjusting the machinery shaft speed, the helium mass flow rate, and by continuously moving the control drums to modulate core heat generation. Now, SimEngine will inject a helium motor malfunction to demonstrate a pressurized loss of coolant. Under this kind of failure, the temperature of the fuel and vessel are the most limiting safety criteria. As the fault is detected, the control drums shut in to terminate the fission chain reaction and the air jacket opens, allowing heat rejection of the pressure vessel via a natural convection current. A small amount of decay heat is still produced by fission products. After the fuel temperature peaks in a few hours, the entire core cools to ambient temperatures. The fuel never exceeds 950 degrees, well below the 1600-degree limit established by trisul fuel qualification. With SimEngine, Radiant is progressively integrating all Kaleidos hardware into this real-time simulation, continuously building a safety case derived from real-world verification. Mechanical, thermal hydraulics, electrical, and nuclear engineering teams are working towards a fuel demonstration in Idaho in 2026. Visit our website and help us build access to clean, dependable, and rapidly deployable power across the world. Let's make nuclear power portable.